I am back with the problem from analytical chemistry this time. It's about conductometric titration. And I want to be honest with you, if you have never studied conductometry before, you are not behind. In fact, that's exactly why I picked this problem, because the students who solve problems like this at the actual Olympiads are not the ones who memorized every electrochemical technique. They are the ones who understood acid base so deeply, so completely, that they could focus into something they had never seen before and still figure it out. And that's what this next hour is about. Not conductometry, but thinking under pressure. So let's get into it. So this is the problem from Analytical Chemistry section of International Mendeleev Olympiad. First thing we need to do is to make sure that we read overall question. Just 1-2 minute investment. That's really important. Just skim through it. We have to check maybe dependency between the parts. So as you can see, it has 1, 2, 3, 4, 5, 6 parts. And are these parts dependent on each other? So there is some piece of information, the piece of information asks you something, and so on. So obviously, for example, in this specific problem, you will need to calculate these values, and later you will be using them. So yes, there's a dependency, but we are going to solve part by part. So it's actually better to focus on one part at a time and solve them in order by making sure that you keep note of the values that you have found in the previous parts in some organized manner, because you will need them later. You will need to refer them later on. So now that we confirmed that we will go part by part, let's focus on the first part. So we need to read the problem first, and as we read, we have to confirm the information symbolically, preferably in terms of variables or formulas. For example, conductometry is one of the oldest electrochemical methods of analysis. Based on measurement of conductivity, we have this. Conductivity is related to the existence of ions. That's how I would write it down. So conductivity, we can see that we can show it using Greek letter, sigma, and this is a proportionality symbol. So basically, conductivity is proportional to ions, is related to the existence of ions. That's what we know from here. Is it going to be useful or not? We are not sure. We are just writing the information in short because we don't have time to read text, right? Whenever, maybe next time in the later parts of the problem, if we need to refer to some information, we just write them in our paper, in our solution box, let's say, so that it's easy for us to refer whenever we need it. So each ion is characterized by molar conductivity, lambda, and here we have unit, which depends on the charge, mobility, then there's mu, and then total conductivity is sum of the conductivities of each ion. So what we need to do here is, before we start this kind of problem, is to do a unit check, just to make sure that everything makes sense. This check needs to be done because later, even from the first question, we will be using those units. So as you can see here, we have two equations that we are given. Lambda, which is the mobility, is equal to charge multiplied by mu multiplied by F. And here we have sigma, which is the overall conductivity. So we need to have this full picture of what is going on. So this sigma, which is the same as this one that we have shown here, is related to the ions, concentration of ions, as you can see here. And also let's do a unit check. So lambda is given as S multiplied by meter square per mole. And this is the multiplication of Z, and there's not any unit for Z because it's just the absolute value of the charge. And mu, and they have mentioned that mu is mobility, S square over coulomb, multiplied by Faraday constant, and the unit of Faraday constant is coulomb per mole. Ideally, you are supposed to know this, but even if you don't, I think it's given in formula booklet. So what we need to make sure is that, yes, they indeed gives this lambda in terms of unit. Columns are canceling out with each other, and you end up with Sm square over mole. And is Siemens. You are not supposed to know this. It's just the conductivity metric, Siemens. But at this point, we absolutely don't need, at least up until now. And then we have sigma, which is the sum of the conductivities. And this is like basically sum of lambda, which has the unit of Sm square over mole, multiplied by concentration, which is mole over meter cube. So this is another important thing that we have to know, because usually concentration is mole over liter, right? That's what we are used to. But now it specifically needs to be in mole over meter cube. That's another thing that we need to take note of, because later we will need to use this concentration in our formula, and you have to be careful because it's not trivial mole over liter. And as you can see, mole cancel out, and meter square, meter cube, you end up with S over M. So everything makes sense, because in analytical chemistry, it's really important to include units in your final answer, how they cancel out each other, how do you get one unit from another. So it's really important that you do this, let's say, mental check before you start. And now we continue. So they ask in the first question, they give us the mobilities, and the mobility is this mu. So they give us the mu's, and they ask us to calculate the molar conductivities, that's the first thing, and conductivity of pure water. So first, we are going to calculate this molar conductivity of OH and hydrogen plus ions, and this is how we need to write our solution. So molar conductivity of hydrogen plus ion is basically equal to this. This is already given to us, and we are gonna just plug in the values. But always make sure that you are writing your answers in this format. So this is our variable, and then the formula that we are given in terms of other variables, and then numerical values for those variables in the formula, and then final numerical answer. So, and in every stage, you need to input the units here. And again, we need to confirm that column and column, they cancel out with each other. You end up with Sm squared over mole. And this is the value for hydrogen. And you do the same, and you end up with the value 0.01997 Sm squared per mole for OH minus. So at this point, it's important to be careful about the units. That's the first thing. Second thing is being able to write our answer in this format. Variable formula, numerical calculations with units, and then final numerical answer again with the units. And now we need to find conductivity of pure water. So we are going to write the formula first. So we need to sum the conductivities of each ion, and the pure water, we only have hydrogen plus and OH because of the protolysis of water. But the thing is that we need to know the concentration of. We already find out the molar conductivities. We know these two. We need to find out this. And because in pure water, they are same with each other, concentration of hydrogen plus and OH minus. So we are going to use the fact that pH is 7 for neutral water at 25 degrees. So that's actually something we need to care about. Even in this question, they haven't mentioned, but we have to assume that it has to be a room temperature so that the pH is 7. And then we are going to find out that that's 10 to the power of minus 7 mole over liter. But we need to convert this trivial traditional mole per liter that we are used to in order to show concentrations to this less trivial form of concentration, which is mole per meter cube, because that's what we are going to use. And if you want to make a conversion, I would suggest to write liter decimeter cube conversion first, because 1 liter is just 1 decimeter cube. That's something that you have to know. And from decimeter cube, we can go to meter cube, because 1 meter is 10 decimeter. That means 1 meter cube is 1000 decimeter cube. Basically, 1 meter cube is 1000 liter. So that's why we are going to divide by 10 to the power of minus 3, and we will end up with 10 to the power of minus 4. And that's the value we are going to plug in here, 10 to the power of 4 mole over meter cube for the concentration, and then sum of the molar conductivities with this unit. And mole, they cancel out with each other, and meter square, they leave us meter. So you end up with S over meter. And you do the calculation, you get this answer, 5.5 almost, 10 to the power of minus 6 S over meter. So that's going to be our final answer. Now we move on to the second question. So we are done with the first one, and this is the overall problem. Now we are going to move to the second question. Again, we have some information accompanied by graph, and then we are going to do this. Of course, you need to make sure that you are really organized so that you have mentioned these values on top of your solution, or maybe after you did this one, you might want to highlight in some way. Probably you will not need to use this conductivity of pure water. You can, but we are not sure yet. So maybe you might want to highlight that this and these two values, and just then this. So whenever you need to refer them later, you can easily use it. So here we read this part. In the first experiment, there's like 50 milliliter of strong acid. They titrate this strong acid with a solution of alkali. And then here we have a graph. It represents conductivity as a function of volume of the alkali solution. So this is the most important explanation for this graph. And now the question is, which ions contribute to the conductivity before the equivalence point, in the equivalence point, and after the equivalence point? And they ask us to assume that water dissociation is negligible. So first, we have to mention what we know, and we need to write them as concise variables and notations. For example, solution of alkali, you can just choose MOH. I usually would have chosen metal OH, but it's a bit controversial because metal OH, if you write it like this, it looks like methanol. So that's why I usually write MOH. But if you explicitly mention that Me means metal, then you can also use metal OH as a notation. It's totally up to you, as long as you are being very explicit about the variables, whatever notations that you are using to represent the stuff, because every single time we are not going to write alkali, right? That takes a lot of time. So in the beginning, you just write this just in the problem booklet. For example, this one here, that equivalence point. So what does equivalence point means? It means that the base that you are adding, the volume of the base that you are adding, is equal to equivalence point. So that's a special point at which you reach to the equivalence. And other than that, you are given the amount of strong acid. So we write as VHA as 50 milliliter, and also the concentration of base that you're using to titrate that strong base, which is 0.5 molar. So you write all of these, and you have to mention, if you are going to use MOH later on, in your solution box, you have to explicitly mention that M denotes metal ion. The better version for this one would be actually MOH. Let's say this small m denotes the potential oxidation state for metal M. So that's actually much better option in this case, because we don't know, is it monoprotic or polyprotic, and if it's polyprotic, how many OH we are having. So this was my first guess, honestly, but there is this better option here, MOH. For example, it could be sodium hydroxide or calcium hydroxide and so on. But from experience, Usually we use, let's say, monoprotic bases like lithium hydroxide, potassium hydroxide, sodium hydroxide in this kind of titration, because magnesium hydroxide, calcium hydroxide, or even aluminum hydroxide, so these are examples of polyprotic bases, they are not as strong as first group metal halides. So that's why there is a really high chance that we will be using monoprotic acid like lithium hydroxide, potassium hydroxide. And also, if you want to go back to the original question, the reason why I specifically chose this as monoprotic base, so if you go back to the original question, you will see that in problem 3, that's why we needed to skim through the problem. In part 3, they say determine the acid, this HA, and alkali. And as you can see, there's only 3 options that they have given us for alkali. So that's the reason why I have included MOH as a notation for alkali that they are talking about. But you can actually also confirm that even in the problem, they set the boundaries for us. So we don't need to consider polyprotic alkalis. But in general, yes, for other questions, for different purposes, let's say, it's good to write this as MOHM. But for this specific question, MOH would be sufficient. All right. And now they ask in the first question, they also gave the graph, but it seems that the first problem is not much relevant to the graph. So they ask us which ions are dominant at these 3 different points. In order to answer this question, just in general, it's good to remind ourselves that there are 3 possibilities whenever there's a titration, because these equivalence point calculations, they need to be done after we find out that which case is it. Is it the possibility 1 where we titrate strong with a strong? It could be strong acid with a strong base or vice versa. So that's actually easiest, and this is the one in this problem because they say that strong acid HA is being titrated with the alkali, and we saw that there are only 3 options for alkali, and they're all strong: lithium hydroxide, sodium hydroxide, and potassium hydroxide. So this is the titration of strong with strong. That's actually easiest in terms of the calculation, equivalent point calculation. Then there could be a case where strong plus weak. It could be either strong acid with a weak base or strong base with a weak acid. And then the last one would be weak acid with a weak base. So there are 3 possibilities when you consider the titration. And the one in the problem is the titration of strong acid with a strong base, which is the easiest one. And then for each possibility that we have 3 points of interest in general: before titration, at the equivalence point, and after the excess base is added, post-equivalence point. So for each 3 possibility, you need to have, this is a skill that you need to have to be able to calculate pH at any point. So we need to analyze each point for the strong plus strong case in the next slide, and we will try to answer this question because actually that's quite easy, but I want you to see the full picture. So this is what we are dealing with, titration of strong acid with a strong base, and we are going to analyze this specific titration type at 3 points of interest during titration. So the first point is before the equivalence point. Anything between 0, V base is 0, and V base less than V equivalence. So as you can see, we have HA and MOA in their initial amounts. We always make sure that they are converted to moles, and then this number of moles of base is less than number of moles of HA, so you consume all of them, you are left with some amount of HA, and you form some MA. And at the equivalence point, you consume all of them because these 2 things are actually same. That's the meaning of equivalence point. These 2 things are equal to each other, so you consume them, you are left with nothing, and you only have MA, your salt. And finally, you have post-equivalence point. You add a little bit of too much of MOH, so you have some excess. So in order to specifically answer for this question, we consider that what we have at the end, because this is the initial, this is the change, and this is the final. So what do we have at the end? We have HA and MA, so that means we have hydrogen plus A minus and M plus that are contributing to conductivity, because if you remember, the first, let's say, equation or half equation that we have used is conductivity, which we show with sigma, is proportional to ions. So that's why we need to check what ions are present, not just for this question, but for the entire question in general. What ions are present at specific point in titration, or just in solution at any point, whatever we are doing, and how we can find the conductivity, because conductivity is directly proportional to this concentration of ions. So this is the first one. The second is at the equivalence point, and at the equivalence point we only have MA, M plus, and A minus are the ones that are going to be contributing to conductivity. And lastly, we have MOH and MA, which means M plus and A minus from the dissociation of salt, and OH minus from the base. So this is going to be our answer for the part number 2. And just for your information, amounts that I have listed here are not important for the purpose of this question, like VH, V base. They don't ask us to do this. This is just overall knowledge. So whenever you have a titration, you need to make sure that you have full control over these numbers so that at any point in titration, you can calculate value or whatever basically feature of solution that they're asking you. For example, in this case, it could be conductivity of solution. Another question, it could be a pH of the solution. It depends on the question that they are asking you. Now we are done with the question number 2, which are relatively easier in compared to the rest of the question. Now we are moving on to part 3. So they ask us to determine the identity of acid, and they have given us some options, and also identity of alkali that's being used in the titration. And taking into account the molar conductivities of ions are as follows. So they have given us the possible ions and their corresponding molar conductivities. So this is the point we need to refer to the graph, because as you can see, we have numbers. We cannot do this without numerical calculations. Basically, time has come to consider the graph, and we will be using the values that we are given, which is the volume of the acid that's being used and the concentration of base. So we just write it here that we know these. And the graph gives information about ion conductivities, which are related to concentration. So it's a conductivity versus the base. So it's actually similar to traditional titration curve. So traditional titration curve is like this, where we have the volume of the base that we use in order to titrate acid. And here is the pH and it changed. So from that, we can relate this pH concentration of the species at any point during the titration. But here, instead of pH, we have another characteristic of solution, which is conductivity. So my point here is that we can use those values of conductivities at different interesting points during the titration to find the concentrations from which we can have some idea about the identity of the ions, because here we need to know the concentration. We also have some information about the conductivities, and then by relating those, we can find the identity of the ion using their molar conductivities. And here, 2 points are useful. So the first is when we don't add any base, V base is 0, and the equivalence point where V base is the same as equivalence point. So equivalence point where V base is we can show it as V equivalent. And as you can see, it's 2.75 milliliter right in between. And if you can see this graph, they already give these grids, which help us to find out this intermediate point. So every written tick here is 0.5, which means the half of it is 0.25. So 2.5 plus 0.25 is actually 2.75. So you should be able to read this from the graph. And now here we see that this point corresponds to equivalence point. And why is that? How do we know that the lowest conductivity in this graph corresponds to the equilibrium? Why it's not here, but it's just the lowest point in this graph? What would be your justification for the drop of conductivity throughout titration? At this point in the titration, in the beginning, when you don't add any base, like when V base is 0, you have only hydrogen plus and A minus. And as time goes by, as titration progresses, and before equivalence point, we have here any point between equivalence point, if we have hydrogen plus, M plus, and A minus. And at the equivalence point, we only have M plus and A minus. So basically, when you go from before the titration starts, which means hydrogen plus and A minus, you go to M plus and A minus. So basically, what happens here, and I will show this very specifically later on because we will need to refer to that in part 6 and part 5. So you basically replace hydrogen plus by M plus. And if you go back to the problem number 1, so the value you have found for molar conductivity of hydrogen plus and also OH minus, they're actually higher than any ion that you see here, especially this M plus. So this gradual replacement of hydrogen plus by M plus, yes, you decrease hydrogen plus, but you also increase M plus, right? So you basically, honestly, you exchange hydrogen plus for M plus. So you could maybe not expect conductivity increase or decrease, but because molar conductivity of hydrogen plus is much higher than these M plus, even for all candidates, that means by replacing hydrogen plus by metal ion, you're actually decreasing the overall conductivity. And when you have the lowest conductivity, that means you completely got rid of hydrogen plus. And actually, that's the reason why you later on you have your increasing conductivity, because you have excess of OH minus. Again, OH minus comes, not again, but when I say again, I mean another ion with high conductivity comes into solution, comes into play, and they dominate these conductivity calculations. That's the full picture of what is going on. And because of that, we just denote this point, the lowest point in this graph, as equivalence point. Were you supposed to know this before? Not really, because when we learn analytical chemistry, we don't learn specifically conductometry or anything about conductivity. But this question is self-explanatory. As you can see in the first paragraph, they already gave information about the units, about conductivity, and how it's related to concentrations. So what you have to know is how titration progresses, what happens in the titration, what are points of interest are important to us, and how to make calculations at those points of interest before the equivalence point, at the equivalence point, and post equivalence point. So combining the knowledge of your titration with this new information that you are presented, you should be able to arrive at this conclusion. So since conductivities are related to concentration, we need to find the concentration of HA to have full control over concentration calculations. And also we can use this V base equal to V equilibrium interchangeably. So this is the equation that we are interested in. And of course, at equivalence point, the number of moles of acid and number of moles of base are same. So this is the equation that we set up, and we find out the concentration of HA. So this equation, this tells us that initial concentration of H and the volume of HA, they should be equal to V base. And here V base, as I said, can be used interchangeably with V equilibrium. And here V equilibrium is 2.75 milliliter multiplied by C base, which is 0.5 molar. We take it from here and then divided by VH, and you get your answer as this. But since we will be doing conductometry calculations, it's important to convert this molar, which is to mole over meter cube, which is actually, at this point, you have to realize that if you multiply molarity by 1000, you can convert it to mole per meter cube. So now we found our concentration of CHA just by simple equality using this equivalence point. So now we know concentration of HA, we put it somewhere else, organized manner. And now we are going to analyze this first point. Now that we know initial acid concentration, we need to analyze this initial point in terms of conductivity. So remember that the conductivity is proportional to ions. So let's analyze the ion content of the solution at point where V base is 0. So we need to analyze this, and we use the fact that HA is a strong acid. They already gave this to us, and there are only 2 ions, hydrogen plus and A minus. We have been saying this over and over again. And these concentrations of hydrogen plus and A minus are equal to each other, which in turn is equal to CHA. So we already know what ions are present, hydrogen plus and A minus. We already know their concentration, which is 27.5. And now we're going to use them in this equation. And at this point, we also are given this conductivity of the solution, which is 1.175. And we will be using that as well. This is our equation. And J, which is the concentration of hydrogen plus and A minus, they are same, multiplied by sum of the conductivities of hydrogen plus. So if you multiply and then this to this, there are 2 conductivities of each ion, and you sum them up, they're equal to 1.175, which we take it from the graph. And by establishing this equation, we find out that the value for molar conductivity of anion is this. But it's good to write this as milli s meter square per mole, because as you can see, all of these values are given in terms of milli, 1000 times more, because that's more convenient to represent this number instead of saying this and knowing 10 to the power of minus 3 every single time. So molar conductivity for our anion is 7.73, which is not perfect match to any of anions that we are given. We definitely know that it's not perchloride ion, so we can maybe eliminate. So we just take note of that. These 2 are possible anions. There are 2 possibilities. And we remember that we also got equivalence point information as well, which brings me to the next slide. So we are going to analyze this point. We are going to look at what happens at the equivalence point, while keeping in mind that anion A minus is one of chloride and bromide. So again, in order to get useful outcome, we need to see how neutralization reaction looks like. And for that, we need to know concentration of salt we get at the end. So this is the neutralization reaction. So we need to find out the concentration of Ma, because that's what dictates the conductivity at the equivalence point. They are the ones that contribute to conductivity of solution at the equivalence point. So we need to find out CMA, and we can easily find out, because we know the equivalence point, what amount of V you need to use, and we also know the concentration of base. So from here, we can just set up this equation and find out the concentration of Ma at the equivalence point. So equivalence volume you need to add is 2.75. We already have used it, and concentration of base is 0.5, and we need to divide it by the total volume of solution, because at this point the total volume of solution is no longer 50 but 52.75, and you plug in all the values in this equation, and you end up with 26.5 mole per meter cube. So now we found out that one as well, and now we move forward to analyze that equivalence point in terms of conductivities. So again, conductivity is the sum of the conductivities of the ions, molar conductivity by multiplied by concentration. So multiplied by conductivity of M plus, concentration of A minus multiplied by molar conductivity of A minus, because just like the strong acid case, Ma is a strong electrolyte, so it actually gives M plus and A minus, and the concentration of Ma is actually same as concentration of M plus and concentration of A minus. So they're all same because we have full dissociation because of being strong electrolyte. And then that's why we make this compact equation, and then we make sure that it's equal to 0.3. And where does this 0.3 come from? If you just follow this line at equivalence point, the conductivity of the solution is 0.3. So you should be able to read these 2 values, 2.75 milliliter and 0.3 S over M for conductivity, just by seeing from this graph. And then you solve for the sum of M plus and A minus, which gives us 11.49. So now that we know the sum of the molar conductivity of cation and anion, we set up this little table, because we know the sum of them, right? Because the molar conductivities of cation and anion. We also have 2 candidates for anion. So these are the 2 pieces of information we found from analyzing these 2 points in the graph. So we make a simple table with a question. What would be the molar conductivity of cation, and thus the identity of cation, if anion is chloride, and the second if anion is bromide? So if anion is chloride, the conductivity of chloride is 7.63, which leaves us 3.86 for M plus, because as you know, the sum of these 2 should be 11.49. So I actually calculate these values by 11.49 multiplied by molar conductivity of A minus. So once I use 7.63, if I think that A minus is chlorine, and once I use 7.8, if I think that A minus is bromine. And based on this, I find these 2 values, and then I check, does any of these values that I get match any cation that we are given here? And fortunately, we have only one match, which is in a perfect agreement. 3.69 does not match to any of cation that we can have among candidates, but 3.86 perfectly match with the lithium. So we find out that this M plus was lithium, and A minus was chlorine. And specifically answer to this question, it says acid. Acid is going to be hydrochloric acid, and alkali is going to be lithium hydroxide. Now, there are two things I would like to mention. You could have done the other way around. You could have started with this point, equivalence point calculation, and you would arrive at this conclusion, and you would find your candidates based on this. So which cation and anion pair would give this sum of molar conductivities? So actually one case would be lithium and chloride. Another possibility is sodium and perchlorate. So if you sum them up, you can also get something really close to 1149. So my point here is that you could have started with this and then could have used the initial point and then to find out that the answer is unambiguously and chloride. But we have used just a normal logic that just let's start V base is 0 and then V base is equivalence point. That's why we did, but you could have done this one as well. That's the first thing I have to mention. The second thing is that you have, even though we find lithium and chloride, but if you do these initial calculations, which we are going to take into account hydrogen chloride, maybe this chloride, using chloride as 7.63 is not going to exactly give us 1.175, because when you use 1.175, you found the answer of 7.7. If you remember, for the molar conductivity of anion. So that's not a perfect match. It happens because this is experiment. There could be multitude of reasons why there is not a perfect match, but we can guarantee our answer is correct in terms of identifying cation as lithium, anion as chlorine minus, because of this information here as well. Just two of them together unilaterally agrees that metal is lithium and anion is chlorine, which makes acid as hydrochloric acid and alkali as lithium hydroxide. We are done with the third problem as well. Now we will be moving on to the first part of the problem, which asks us to calculate the conductivity of solution after we add 6 milliliters of alkali solution. So they ask us to calculate the conductivity of solution when we add 6 milliliters of alkali solution. So we write down what we know: concentration of acid, concentration of base, volume of acid, and how much base we need in order to reach equivalence point, and how much base we are adding right now. And we also need to find out that when you add 6 milliliters of alkali, total volume of solution is going to be 56. And also from this comparison of these two values, we can see that this is post-equivalence point, because we have added more base than we need, basically, to reach equivalence point. So this is going to be post-equivalence point calculation. And we also write it here. These are actually, for example, this one and this one, I suggest you to write them in, let's say, in your solution box, some to top right or whatever, so that you can easily refer to whenever you need it. So that's what I was telling you before, that it's good to mention certain variables that you find out during your solution so that you can easily refer to them later on. And since this is after equivalence point, we are going to use this kind of calculation, basically table, reaction table, where you have more base and you have ended up with accumulation of lithium hydroxide. And we can easily calculate this with the given values, which is 1.62 millimole, because we know V base, which is 6 milliliter, we know C base, which is 0.5, and you minus VHA, which is 50 milliliter, and 0.0275 for the concentration of HA. And here we find out that the amount of lithium chloride left is 1.3 millimole approximately. And I'm using millimole here because that's more convenient. As you can see, this is a multiplication of molar by milliliter. And what is molar? Molar is actually mole over liter. And of course, you need to convert milliliter into liter in order to make sure that this multiplication works. But as I mentioned several times before, that you can use it as millimole per milliliter, because honestly, there is no difference between mole per liter and dividing both numerator and denominator by 1000. So mole per liter is same as millimole per milliliter. So that's why that makes this calculation really easy, provided that you mention your answer in terms of millimole. So once we find out the number of moles of lithium hydroxide and lithium chloride, we can find their concentrations, because that's what we are interested in. So we just divide basically quantity in terms of millimole divided by volume in milliliter, and we divide it by total volume. And actually, you can once again confirm that you really don't need to convert these milliliters into liters, because honestly, I find them really annoying to divide these small values by 1000 to get something like 0.0 something. That's really, really annoying. So this once again shows that it's actually okay to keep the milliliter, provided that you are aware of the fact that you are getting millimole, and later you can divide millimole by milliliter again to get molar. There's nothing that prevents you from doing that. So that's perfectly acceptable, and that takes a lot of time. So this is like a small note I would like to mention to make your calculations easier. So we find the concentration of lithium hydroxide and lithium chloride, but it's really important that we convert them into mole per meter cube, because that's what we will be using them. So at this point, again, you have to be confident that if you multiply molarity value by 1000, you will get mole over meter cube. And now we finally set up our equation to find the conductivity of solution, which is going to be concentration of ion multiplied by molar conductivity of ion. And at this point, we have metal ion, anion, and OH, because we are accumulating OH minus, because it's post-equivalence point. And basically, we know all of the values, right? We know the concentration of the species, and we also know the molar conductivities of these ions, and we set up our equation. And here there is one important thing that we have to take note, that concentration of lithium is actually sum of 29 and 24.9 because both of them has lithium. That's actually really easy to see. Lithium OH also gives lithium plus and OH minus, and lithium chloride also gives lithium plus and chloride minus. So that's why if you want to find out the concentration of lithium, you need to add the concentration of lithium hydroxide and concentration of lithium chloride. That's why this addition is here, multiplied by 0.86, which I take it from this little table. That's molar conductivity for lithium. Chlorine minus is the same as lithium chloride concentration, which is 24.6, and then multiplied by the molar conductivity of chlorine, which is 7.63. And here we are going to use the value that they are given, not the value that we found as 7.7, because that's probably some experimental error. And then we continue this equation by adding the concentration of OH, which is 29, which comes from lithium hydroxide, and this value, which we found in part 1. And you get this value, which is in terms of milli s over meter. But honestly, they just say calculate solution conductivity, and it's perfectly fine to just give answer like this. I just converted it to s over meter because we have used that during entire question, s over meter, and this value is much more sensible in compared to the conductivity values we have been using. For example, 0.3 at equivalence point, 1.1 when you start, before the titration starts. But this kind of notation makes much more sense. So this is the final answer for the conductivity of solution when you add 6 milliliter of alkali. And now we are done with part number 4 as well. Now we are going to do problem number 5. And before that, they have given us some information. So they did a second experiment. So this time you have a mixture of hydrochloric acid, which is a strong acid, and a weak organic acid. And they have given a Ka of acid as well. So they make a mixture of 20 milliliter, and then they dilute it to 100 milliliter, and then they do titration with a strong base. And then they give the result of titration in the form of table. This time it's not a graph, just a table, but it's the same idea with the graph. If you want to construct a graph out of this table, it's the same idea. In the x-axis, you are going to have the volumes of the base that you are adding, and this is the conductivity. It's exactly the same form in terms of variables with the graph that was presented in the earlier parts of the problem. And you have the conductivity value, conductivity of the solution for each milliliter of the base that you are adding. So the first question is, how many protons of weak acid have been titrated? I will admit that this is a bit weirdly put. So they could have just asked how many protons of this polyprotic acid have, or there was no need to put H and B. They would just say, oh, there's polyprotic acid, and how many protons does that polyprotic acid have? So, but saying that how many protons of H and B have been titrated actually arises question, right? Oh, there is maybe n protons, but only maybe 2 of them have been titrated, or maybe they're asking to find the value of n. So that's another question. That's a bit weirdly put, honestly. But when we solve them, when I show you the solution and how to get there, you will realize that maybe at this point it's a bit weird, but it will not be important when we reach to that point of calculation and understanding. It's also weird that they have only given 1 Ka, so that it should have been maybe Ka1, so that we can know that there are more protons, so n is higher than 1, and now we need to find the value of n. Or it could be the case that n is higher than 1, but let's say n is 6. There's 6 protons in the acid, but only 2 of them have been titrated. So that's also a possibility. Before we start calculation and analyzing the table and the values here, we have to understand the dynamics of the process when the mixture of acids is titrated. So here, as you can see, this is a mixture, not a single strong acid or not a single weak acid. So it's important to realize that strong acid reacts first, and this is followed by the weak acid neutralization. So that's the first and the most important thing. And I will tell you 2 reasons why I want to justify this, why when we have a mixture of strong and weak acids, why are we having strong acid going to titration first? The first reason why this holds true is because if you just compare hydrochloric acid, so as far as I remember, it has a pKa of -7, which means it immediately dissociates into hydrogen plus and chlorine minus, let's say Ka value of 10 to the power of 7, which means pKa is -7. And let's say another acid, which is, I'm just going to show it as HA, and it's going to be dissociated into hydrogen plus and A minus, and we are just going to assume that Ka is 10 to the power of -5, like in this case. And what's going to happen is, if hydrochloric acid is being dissociated, so we will have 2 equations. Hydrochloric acid goes to hydrogen plus chlorine minus, and hydrogen plus is being neutralized by OH minus to go to H2O. So for this, it's Ka is equal to 10 to the power of 7, and for this, it's going to be opposite of Kw, right? So we just can write it. I'm trying to be quantitative here. K equilibrium here is going to be the 1 over Kw, which is 10 to the power of 14. And when you add them up, hydrogen plus, they go, so you end up with hydrochloric acid titration. So it goes like hydrogen. So for this, K equilibrium final is 7 plus 14, which is actually 21. That's really huge number. You can do the same calculation for HA. So we can start with HA going to hydrogen plus A minus. They're characterized by Ka value of 10 to the power of -5. And that hydrogen plus is reacting with OH minus, going to H2O. Again, here K equilibrium is 10 to the power of 14. And when you add them up, you get the neutralization of HA by OH minus. This hydrogen plus are cancel each other. And you end up with the neutralization of weak acid. And the K equilibrium value here is 10 to the power of 9, 14 minus 5. So both of these numbers that we get are really large. So that's why we say that it doesn't really matter as long as you don't have extremely low Ka value. No matter how weak acid is, whenever you titrate acid with base, whether it is strong acid or moderately weak acid, you will get really high K value. And because of the fact that they have really large K values, these are essentially irreversible, essentially goes to the completion. But the thing is that if you compare these two cases, 10 to the power of 21 is extremely larger in compared to 10 to the power of 9. So that's why this neutralization dominates. If I'm adding base to the solution, that base would like to react with hydrochloric acid rather than this weak acid. So that's the first reason I would like to use in order to justify that strong acid is neutralized first. And the second thing I can use is, even without neutralization, just let's say we try to analyze the solution. And then we have hydrochloric acid and HA. Because hydrochloric acid immediately dissociates, we observe full dissociation here. And here we are going to have an equilibrium characterized by Ka. Because we are going to have more hydrogen plus in the solution, here it's going to be really high, the concentration. And according to Le Chatelier principle, it will go to the left. So we can say that strong acid suppresses the dissociation of weak acid because of high concentration of hydrogen plus in the solution. So first reason was that we really have larger K equilibrium. So let's just call it as larger K neutralization for strong acid. That would be the first reason. And the second reason is that strong acid suppresses weak acid dissociation. So net result is that your initial solution features, it could be pH, conductivity, and so on. In this specific problem, we are talking about conductivity, but you can actually extend it to all solution features. They are almost solely determined by strong acid only. So let's say you want to calculate the pH of the solution. I'm not talking about titration. I'm just talking about the pH of the solution of mixture of weak and strong acids, right? So that's going to be determined by strong acid, and same as conductivity and probably some other features too. So that's really important to set this up before starting the calculation. And now that we know this, we are going to continue with this problem. So this is how the graph looks like. Let's analyze this graph, which helps us to correlate this specific feature of the solution, which is conductivity in this case, at any given point, to the content of the solution at this point. We have already analyzed it when we solved the second subproblem, when answering which ions contribute to the conductivity at different points during the titration. So initially, we only have hydrogen plus and chlorine minus. As we go towards the equivalence point, we are slowly having lithium plus as well, because if you remember, this was hydrogen chloric acid being titrated with lithium hydroxide. And at the end, here, we only have lithium plus and chlorine minus. So the net result is that we gradually replace hydrogen plus with 35 molar conductivity with lithium plus, which is just 3.8. So just because of that, what happens is that conductivity decreases. So I wanted to show the original graph presented in the problem to understand the strong acid case. And now we are going to construct our own graph for the mixture of strong and weak acid. So this part is going to be same. This is the first part of the graph. And by the way, this graph is just like a theoretical graph. Those points are not real points that I got from the table. It's just for you to understand the full picture of the case of the mixture of strong and weak acid. So as discussed before, this first part is the same as that of the strong acid, because strong acid neutralizes first, and during the titration, till the equivalence point of the strong acid, conductivity decreases, as shown before. In the second part, where the neutralization of weak acid starts, even though we might expect a similar trend to the strong acid case, the observation is quite the opposite. When the weak acid starts being neutralized, we see the increase in conductivity, which is opposite to the case of strong acid. So let's imagine that it's monoprotic weak acid. We only have one proton, like HA. And at this point, we have only HA. And M plus and chlorine minus, they just come from the previous titration of strong acid, as you can see here. Because when you finish the neutralization of the strong acid, you are only left with the metal ions, cations, and the anions that come from the strong acid. So here you have the M plus and chlorine minus that comes from the previous titration, and only HA, so the conductivity is quite low. But as the titration happens, you are having A minus, M plus and A minus, and I haven't written M plus again because we already have that from the previous titration. So most importantly, this increase in the conductivity, it's all about the formation of A minus. So this is the part that is different from that of strong acid. So strong acid titration is accompanied by the replacement of hydrogen plus by the metal ions, but weak acid does not have that hydrogen plus initially. Weak acid is just in the form of HA, maybe slight dissociation, so hydrogen plus concentration is really low initially, but we just kind of accept that there is, let's say, almost no dissociation or not observable high conductivity because we really have low concentration of hydrogen plus and A minus. So it's mainly dominated by HA initially, but as titration goes by, you have this equation, right? You have HA that reacts with OH minus, it gives some A minus plus H2O. And this part of the titration, here we have in the solution as H dissociation to A minus and some A minus, and obviously hydrogen plus as well. But this is the thing that is most important in this point of the graph. So the conductivity trend for the weak acid is opposite of what we have expected. So if you compare the initial point of the weak acid titration and the last point of weak acid titration, what happens is HA is replaced by A minus, and also you increase the concentration of M plus because you are adding more and more base in the form of M plus and OH minus, and M plus is just, let's say, hanging out there, right? It doesn't interfere with the neutralization. It's just concentration increases. So because of this, we are observing the increase in the conductivity. And in the last point, after complete neutralization of both monoprotic acids, so we just accepted that both strong and weak acid are monoprotic just for the sake of building this theory, we see drastic increase in conductivity since we keep adding the base. So here, high conductivity is governed by excess OH ions. So here you have accumulation of OH minus, so that's why an OH minus also has high molar conductivity as we have calculated in the first subproblem. So this is just like in the case of strong acid. This is like a post-equivalence point. And in this specific case, we are interested in 2 points. First is the intersection of this first and the second segment. This part is important as they decide the equivalence point for each acid. V1, which is the intersection of the first and the second linear segment, it corresponds to the neutralization of weak acid, and V2 corresponds to the neutralization of weak acid. V2 is actually the sum of them, because let's say V1 is like, let's say 5 milliliter and this is 7 milliliter. So that means this is actually 7 minus 5, 2 milliliter. So 2 milliliter have been used for the weak acid. So that is what happens when the mixture of acids, especially strong and weak acids, is being titrated, specifically for conductivity, but you can obviously extend this to the pH or other solution features that you might see in the problem statement. So I would like to also mention this beauty of conductivity titration. This is used for determining the concentration of mixture of acids in a very convenient way. And here special care is not required at the end point because it's just determined graphically. Because when you do titration and you measure pH and stuff, you have to be really careful, and you also have to add indicator to detect the endpoint, and sometimes endpoint does not perfectly match. Most of the times they don't match each other, endpoint and equivalence point. Endpoint is most of the time is a bit higher than equivalence point because endpoint is determined by your eyes, the visual cues that, oh, you see the indicator change the color, so that means this is the neutralization point. So you don't need any of that here. So you just have a mixture, you add your base, and you just measure the conductivity with some tool that you have that's designed to measure the conductivity. That's it. You get your graph, you get your linear segments, and by the intersection of those linear segments, you find your neutralization point. So it doesn't even require indicators. And that's the point I think the problem tries to prove. And also you end up learning something new about this conductometry. All right, now let's go back to the original question. And before continuing, I would like to answer to your potential question. Did you have to know all of these? And answer is no, not necessarily. But you were already supposed to know about pH calculations during titration. You remember 3 cases, 3 possibilities. 3 cases, a titration of strong acid, strong with weak, or weak with weak. And 3 possibilities during the titration. Actually 4 points during the titration. Before titration starts, at the equivalence point, and post-equivalence point. So you have to understand all of them. They are in the textbook, right? And so that you have a full picture, full understanding of how different solutions, strong acid solution, weak acid solution, mixture of them, or buffers, etc., behaves by themselves or during titration, so that you can extend those concepts whenever necessary, just like in this problem. So as for this subproblem, you are not supposed to draw the graph. You just need to take a delta ratios, change in conductivity per change in volume. And that's going to give you the rough slope, the derivative. This represents the slopes. And based on that, you can see that the curve consists of certain number of linear segments. So as you can see, these are our volumes that we add, and these are the values. And you can actually just find the difference between these two and difference between these two and divide them, get your first value. You do the same for the second and difference between these two, and you put it here, and so on. This continues like this. And luckily for you, all of these differences that you see here, they're just 1. So you actually need just to take the differences between the consecutive points. You can just find the derivative without having the need to draw the entire graph. And based on this, you can find that there are 3 linear segments. By observing these values of delta, which actually these are just slope points, you can see that that's my first linear segment, that's my second, and this is my third linear segment. There is no any other segment, and this is just in between. That's probably like, you know, this goes decrease, and then in between 3 and 4, you hit the minimal point, and then you decrease again, and then you have drastic increase. And now from this table, we can just see that linear segment 1 corresponds to the titration of strong acid. And at that time, association of weak acid can be neglected. Second segment corresponds to the titration of weak acid. And then you have this accumulation of OH points. So both acids have been neutralized, and you see this drastic increase in the conductivity. So as the curve has only 2 inflection points between linear segment 1 and 2, I will explain what inflection point is. And between segment 2 and 3, you have another inflection point. And the first one corresponds to hydrochloric acid. We can say that there's only 1 proton of weak acid that is titrated. So that's the answer to our subproblem. They ask you how many protons of weak acid have been titrated. We just say that only 1. The answer is 1. So I just want to talk more about this. How would the values look like if there was more than 1 proton? Well, you would have more linear segments, right? Let's say it just continues. Maybe they would give you an extended graph and you have more and more linear segments. So in order to see this picture, I would like to give examples, standard examples from the textbook. For example, this is just a titration of strong acid with strong base, and this is just the pH and the volume curve, and this is the inflection point. This is the point where the derivative is the highest. And this is what you were supposed to know so that you can extend it to other solution features. When I say features, I'm talking about the pH, conductivity. So pH is always given in the textbook. You're supposed to know this. And depending on the problem type, you can extend it to this conductivity and other features of the solutions that they give you. So this is the point that's called the inflection point. And of course, there's another example of polyprotic acid. So as you can see, as we titrate, let's say like this is, for example, just by looking at this graph, you should be able to immediately say that, oh, this is actually triprotic acid. There are 3 protons that are being neutralized by a base. And the points like that corresponds to equivalence points are inflection points. At these points, the derivative is highest. So delta pH over delta V is the highest. So that's why we did this delta sigma, delta conductivity over delta V, to find out the different values of the slope and how the values of the slope change throughout the titration. So my point of showing these 2 graphs is to tell you that you were not supposed to know about conductometry, but you were supposed to know about this, and you should be able to extend the ideas behind these curves to other curves. So for this question, you don't need to do any calculation. Calculation you need to do is just the calculation of those delta sigma over delta V. But that gives you just the fact that, oh, there are 3 linear segments. There are 2 inflection points. So 3 linear segments means 2 inflection points. First one corresponds to the neutralization of weak acid, and second one corresponds to the neutralization of weak acid. And because there's only 1 inflection point for the weak acid, that means there's only 1 proton of weak acid that we are titrating. So we also solved question number 5. And now we have to do calculations for subproblem 6. We have to calculate the concentration of both acids in the original solution, in the 20 milliliter solution. Because remember, there's additional dilution here from 20 milliliter to 100 milliliter, and then titration. So since we know this overall dynamics of how this titration is going to happen when you have mixture, right? We know that there's 3 linear segments. We already found out from the table, and based on that, we find out that there's only 1 proton of weak acid that's being titrated. So that corresponds to 3 segments. And then the intersection of those segments actually gives us information about the exact equivalence point. So that's why the first step is to find the intersection of those linear segments, and then they correspond to those equivalence points for strong and the weak acids. First equivalence point corresponds to the neutralization of the strong acid. Second intersection point is the sum of the equivalence points, sum of the volumes necessary to titrate strong acid, because you already titrated the strong acid, and then you add a bit more, and then you are done with the titration of weak acid. So these are the order of the steps we have to follow. Intersection of the linear segments, which are equivalent to those equivalence points of the acids. And then from those equivalence points, we can do just initial concentrations, just like we did in previous subproblems. So here are the linear segments, and here is the graph. So we already know that this linear segment 1, it's this part, and linear segment 1 is this, the neutralization of weak acid, and then the third linear segment, number 3, corresponds to this, basically where the conductivity calculation is dominated by hydroxide ions. So now we focus on the first linear segment, which is this part, right? And now we just need to find an equation for the line in the form of y equal to ax plus b. It's so easy because we have data points, and according to mathematical rules, we have this line which is 2-dimensional, and we only need just 2 points in order to be able to solve for the equation of the graph. So we have a linear graph, which we know that is in the form of y equal to ax plus b. What we need to do is to find those a and b. First, you need to find the slope. We already found the slope, right, which is 0.111, but a negative one because it's decreasing. So the slope should be negative. And we found the value of a. It's just the slope. Actually, we will do the same for all linear segments because we already know the slope values in all 3 segments. And actually, that was the indicator that helped us to actually separate these table into 3 segments, right? Separate this graph into 3 segments based on those slopes. So slope is easy to get. For the value of b, for example, easiest one would be where x is equal to 0, your y value is b, and the b you just take it 0.6. You can actually use x equal to 1 and y equal to 0.489. You can find the value of b. It doesn't really matter which of these 3 points you are using. This is the easiest one because the value of x, and you treat this x and y. So the value of x is 0, then this 0.6 is just directly your constant b. So the equation for this is just what you see here, that minus 0.111x plus 0.6. Now we are moving on to the second linear segment, second part of the graph that corresponds to this titration of weak acid, this part. And still, we are going to use the same idea. Our slope is already known. And actually, I took the intermediate value between these two. And even though this value is negative here, but this is positive because, as you can see, this is increasing, right? So it makes perfect sense to have this positive value of slope. So here we found the value of slope, and for the value of b here, it's so easy. We can just take the value of x is when 4 and the y is 0.233. We can calculate b. You could have used the value of 5. It doesn't really matter. And this is the equation for this linear segment, and you can do the same for the third linear segment. So here again, your slope is 0.1165, which is just the average of these values, and you can use any point to find the value of b. So here I always use the first value, like 6 and 0.324, and then I find the value of b, and from that I get the equation. So my a is 0.165 x minus 0.666, which is the value of b. And now I want to find the value of v1, which is the amount of the base needed in order to reach the equivalence point for the strong acid. So what do I need to do? Just make these equations equal to each other and then find the value of x. That's it. And then if I want to do the same, I already know the equations for this linear segment. So second and the third linear segment, intersection of them is where they are equal. So I make them equal and I solve for x, and that's 6 milliliter. That's it. And if you go back to the order of the steps that we have to follow, we already find the intersection of the linear segments 1 and 2, which is 3.5, linear segment 2 and 3, which is 6. So that means v1 is 0.3.5 and v2 is 6. And then we have to calculate the initial concentrations, and we have to write what we know. We know the initial mixture because there is some dilution here, right? From 20 to 100, there's 5 times dilution here. So mixture of acids initial is 20 milliliter, mixture of acids final is 100 milliliter, and the concentration of the base that we are using in order to titrate it is 0.6. So I'm just writing what we know, and then because I usually would love to see what I am given and how I will be using them. And also there is one thing that you might use, just 3.5 is fine. That's just the amount of the base for you to add in order to neutralize hydrochloric acid in the mixture. But it could be misleading. You might think that the 6 milliliter is the equivalence point for weak base, but it is not. It's actually 6 minus 3.5 because you have your mixture, you have hydrochloric acid and your H and B, and then you add 3.5 milliliter of base. This hydrochloric acid suppresses the dissociation of weak base that we discussed this before. So this is being titrated, and then you keep adding another 2.5, right, in order to titrate this guy, this weak acid. So in total, it's 6 milliliter, right? So that's why we have to make sure that V2 minus V1 is actually the volume of the base we need to reach the equivalence point. That's it, and these are the values that we know, and we are just going to do our typical titration calculation, which is HA, potassium hydroxide, and equivalence point. They are equal to each other. So we are going to equalize them, and that's just going to give us the answer. Number of moles of hydrochloric acid is the same as the number of moles of base. VC. We're just going to convert number of moles to volume multiplied by molarity. And then the concentration of hydrochloric acid is just calculated this amount of the base multiplied by the concentration of base. And this numerator of this is just gives us the number of moles of base. And then we divide by 100 milliliter because we use 100 milliliter because that is just a volume, right? Volume is like, if I have a mixture, I am just using the overall volume. If I want to calculate the concentration, let's say I have a mixture and that's 100 milliliter. Let's say 5 different solutes in this solution, right? I have A, B, C, D, E, right? And if I want to calculate the concentration of A and concentration of B, concentration of all species in my solution, I am going to divide the number of moles of each guy by the same 100 milliliter. That's how we calculate the concentration. We're not saying that this A only has this 20 milliliter, maybe C has just 30 milliliter, this B has 10 milliliter. No, we are dividing by the overall volume. So that's why I have written here as VHCl, but here actually this VHCl is just this mixture 100 milliliter because I'm using 100, not 20, because we start with 20, we dilute it to 100, and we titrate that 100 milliliter. So that's why I'm using that 100 milliliter. So I find out that the concentration of hydrochloric acid in the 100 milliliter mixture is this, and then I do the same for the weak acid, right? And this time, all calculation here is the same except that this is 2.5, just like the equivalence points that I am using from here, and I find the concentration at 0.015, and then I use this dilution calculation. This is the very famous equation, C1V1 equal to C2V2, and in this case, there is 5 times dilution. So just by calculating the concentration in the final solution by 5 is going to give us the concentration in the initial solution, because we are going from 20 to 100. The concentration in 20 milliliter should be much higher because it's less volume, more concentrated, right? And then I multiply both values by 5, and these are my final answer, 0.105 and 0.075 molar. And that's the end of this subproblem and this whole problem. So, conductometric titration, a topic most of you probably have never formally studied, and yet you just solved the full Mendeleev Olympiad problem using it. And that should tell you something, that the sailing in Olympiad chemistry is not how many techniques you know, it's how far you can stretch the things you already understand. In this case, pH, acid-base, equilibria, ionic behavior. If you understand them truly and master them, practice them, the problems like this stop being intimidating. They actually become interesting. I will see you in the next one. Take care.